Okay, so good day to all of you. So we're already on the seventh chapter of the operating systems lecture. So we have synchronization examples. So for chapter 6, we have the synchronization tools. So now we will having this synchronization examples for this chapter. So let's start our discussion. So again, chapter 7 is all about synchronization examples. So the objectives of chapter 7 are explain the bounded buffer, readers writers, and Dining-Philosopher synchronization problems. Describe the tools used by Linux and Windows to solve synchronization problems, and illustrate how Posix and Java can be used to solve process synchronization problems. So the classical problems of synchronization, so these are the most popular classical problems in the operating system. So first is we have the bounded buffer problem, readers and writers problem, and the Dining-Philosophers problem. So this classical problems is used to test newly proposed synchronization schemes. So let's deal first with bounded buffer problem. So for bounded buffer problem, we have n buffers. Each can hold one item. We have semaphore mutex initialized to the value 1, semaphore full initialized to the value 0, and semaphore empty initialized to the value n. So this is the structure of the producer process. So this is the code. So we have a while loop, and then it uses the wait and signal because it's a semaphore. Then the structure of the consumer process. So it also uses the wait and signal functions. So as you can see with regards to the code of the producer and the consumer process, note the symmetry between the producer and the consumer. We can interpret this code as the producer producing full buffers for the consumer, and then another one is the consumer producing empty buffers for the producer. So as you can see, they are symmetrical with each other. Okay, next is we have the readers-writers problem. So a data set is shared among a number of concurrent processes. So we have readers only read the data set. They do not perform any updates. And then we have writers. They can both read and write. So what is the problem with readers writers? Allow multiple readers to read at the same time. So only one single writer can access the shared data at the same time. And several variations of how readers and writers are considered all involve some form of priorities. So these are the shared data. We have the data set, the semaphore RW underscore mutex initialized to 1, semaphore mutex initialized to 1, and integer read underscore count initialized to 0. So this is the structure of a writer process having a while loop. It also uses the wait and signal, which you can see for the semaphores. And then we also have the structure of a reader process, which uses also a while loop. So note that the writer is in the critical section and n readers are waiting. Then one reader is queued on RW underscore mutex and n minus 1 readers are queued on mutex. Also observe that when a writer executes a signal, okay, so we have here the signal RW underscore mutex, we may assume the execution of either the waiting readers or a single waiting writer. So the selection is made by the scheduler. So the variations of readers writers problem. So the first variation, no reader kept waiting unless writer has permission to use shared object. And second variation, once writer is ready, it performs the write ASAP. Both may have starvation leading to even more variations. So problem is solved on some systems by kernel providing reader-writer locks. Okay, another classical problem is we have the Dining-Philosophers problem. So we have here an illustration, 5 chairs, and then we have plates, and we have a bowl of rice in the middle, and then we have uh, it's not a pair. Actually, these are a chopstick, not a pair of chopsticks. So a chopstick. So you can assume that this philosopher may be Chinese or Japanese or Korean or any other nation that uses chopsticks for eating. So because it's philosopher, maybe it's Chinese because there are many Chinese philosophers. Okay, so enough with that. So what is the situation or the context of the dining philosopher's problem? So philosophers spend their lives alternating thinking and eating. So for this assumption, um, they cannot think and eat simultaneously. If they're thinking, they are thinking. If they're eating, they are eating. Don't interact with their neighbors. Occasionally try to pick up two chopsticks one at a time to eat from bowl. So need both to eat, of course. If you're going to use a chopstick, if you're familiar with using chopsticks, you should have a pair, not just a one chopstick. So, so need both to eat, then release both when done. So in the case of five philosophers, so shared data, of course, is the bowl of rice, which is a data set. And semaphore chopstick, we have five because it is one, two, three, four, five. Five chopsticks initialized to one. So this is the code. So it's the semaphore solution for the dining philosopher's problem. So the structure for philosopher I. So we have a do while, wait chopstick I, that's the first chopstick, and wait chopstick I plus 1 modulo 5, this is the other chopstick. If the philosopher has acquired both chopsticks, so eat for a while, and then for the signal, so the philosophers already finished eating. This is for the first chopstick and the second chopstick. Then, of course, the philosopher will think for a while. So this is the solution for the dining philosopher's problem. So by means of this solution, what is the problem with this algorithm? So for this algorithm, although this solution guarantees that no two neighbors are eating simultaneously, it nevertheless must be rejected because it could create a deadlock. So how can this have a deadlock with this solution? Suppose that all five philosophers become hungry at the same time and each grabs his or her left chopstick. Okay, they all grabbed first the left left chopstick on their side. All the elements of chopstick will now be equal to 0 because it's already, for weight chopstick, it's already acquired by the philosopher. So when each philosopher tries to grab the right, the right chopstick, he or she will be delayed forever. It's just the same with the example that I've mentioned in chapter 6. For example, if you have the pencil and your student A has the pencil and student B has the paper, since you've already acquired both of the processes, one for the other, you're just waiting for the other to give up or give in their resource. It's also like this with the dining philosopher's problem. Since you already have the left chopsticks, the philosopher already acquired the left chopsticks, they only need the right. But since at this they grab the chopsticks all at the same time, so for one philosopher to eat, one should its neighbor should give up, specifically the one on the right or on the left, for that philosopher to eat when he or she is hungry. So again, the problem with this algorithm, it can have a deadlock. So next is we have the monitor solution to dining philosopher's problem. So they added pick up operation or functions and then put down. So that's their solution for this problem. So each philosopher, so how it is done? So each philosopher before starting to eat must invoke the operation pick up, so picking up the chopsticks. This act may result in the suspension of the philosopher process. After the successful completion of the operation, the philosopher may eat. Following this, the philosopher invokes the put down operation. Of course, if the philosopher picks up the chopsticks, the next should be he or she must put down the chopsticks so that other philosophers can use it if others want to eat. So each philosopher I invokes the operation pick up and put down in the following sequence. Of course, we have this dining philosophers that pick up I, so then eat, and then dining philosophers that put down I, then it's finished eating. So this is in this sequence. Of course, you cannot put down something if you did not pick up anything. Okay? So no deadlock. So the solution, it has no deadlock, but starvation is possible, because what if philosopher 1 is always the one who wants to eat? How about the others? So next is we have kernel synchronization for Windows. So uses interrupt masks to protect access to global resources on uniprocessor systems. It uses spin locks on multiprocessor systems, so spin locking thread will never be preempted. Also provides dispatcher objects to be used and which may act as mutexes, semaphores, events, and timers. So events, an event acts much like a condition variable. Timers notify one or more thread when time expired. And dispatcher objects are either signaled state, which is the object is available, or non-signaled state, or the thread will block. So this is an illustration of the state of the mutex dispatcher objects. So for going to the non-signaled state, going from the non-signal state going to signaled state, so the condition for it to be signaled state is owner thread releases mutex lock. And then from signal state going to non-signal state, the condition will be thread acquires mutex lock. Okay, so next is we have Linux synchronization. So for Linux, so prior to kernel version 2.6, disables interrupts to implement short critical sections. So version 2.6 and later, so we have fully preemptive. So Linux provides semaphores, atomic integers, spin locks, reader-writer versions of both. On single CPU systems, spin locks replaced by enabling and disabling kernel preemption. So it is already mentioned that Linux uses atomic variables. So we have this type, atomic underscore t is the type for atomic integer. Then, for example, consider the variables atomic underscore t counter and int value. It means if you are going to add atomic underscore t for counter, it means that the operations of counter must be uninterruptible. So this is, we have an example. So atomic underscore set and then ampersand counter 5. So you're going to set counter to 5. Then this is, you're going to add 10 to the counter. Then subtract 4 from the counter. And then increment the counter by 1. And then value is equal to atomic read ampersand counter. So this atomic operation just means that if you're going to put atomic in their operations, or rather in the variable, so this is a function, it means that it is not uninterruptible. So it's very important for this variables that needs frequent updating. Okay, next is we have the Posix synchronization. So Posix API provides mutex locks, semaphores, and condition variable. It is widely used on Unix, Linux, and Mac OS. So the Posix mutex locks. So how are we going to create and initialize the lock? So we have this library. Number sign include pthread.h. So pthread underscore mutex underscore t mutex. So we have this comment, create and initialize the mutex lock by using pthread underscore mutex underscore init, means initialize. And then its parameter is ampersand mutex and we have null. And how about acquiring and releasing the lock? So this is the code that will be used. So acquire the mutex lock is we have pthread underscore mutex underscore lock and ampersand mutex. Then, of course, it will go to the critical section. While releasing the mutex lock is pthread underscore mutex underscore unlock. Then the parameter is ampersand mutex. So we also have Posix semaphores. So Posix provides two versions, the named and unnamed. Named semaphores can be used by unrelated processes, unnamed cannot. So for POSIX name semaphores, for creating and initializing the semaphore, so we have this library. So number sign includes semaphore.h. Then we have sem underscore t pointer sem. So to create the semaphore and initialize it to 1, so this we have this variable sem is equal to sem underscore open. So sem, the parameter is sem, then 0 underscore create and then 0666 and then 1. These are the parameters. So this is for creating and initializing the semaphore, the sem underscore open. And then another process can access the semaphore by referring to its name sem, the SEM capital, all capital letters. And then next is acquiring and releasing the semaphore. So to acquire the semaphore is we have the sem underscore wait and then the semaphore. Then, of course, it will undergo its critical section. And then we have the release the semaphore is sem underscore post and the corresponding semaphore. So this is for POSIX named semaphore. How about POSIX unnamed semaphores? So creating and initializing the semaphore. So for this, we have library, number sign includes semaphore.h. The only difference is that for unnamed semaphore, sem here is not a pointer. So compared again to POSIX named, it is a pointer. And then to create the semaphore and initialize it to 1, so sem underscore init, we have ampersand sem 01 as its parameter. Compared with named semaphore is we have sem underscore open. So acquiring and releasing the semaphore, to acquire the semaphore is we have sem underscore wait, and then we have an ampersand sem for the semaphore. So actually, they're just the same. It's just that the unnamed semaphore has an ampersand on the name of the variable for the semaphore. They're just the same. Sem underscore wait for acquiring the semaphore and releasing the semaphore is sem underscore post. Okay, next is also we have POSIX condition variables. So since POSIX is typically used in C, C++, and these languages do not provide a monitor, POSIX condition variables are associated with a POSIX mutex lock to provide mutual exclusion, creating and initializing the condition variable. So we have to declare, so we have pthread underscore mutex underscore t mutex and pthread underscore cond underscore t cond underscore var. And then to initialize the mutex is we have pthread underscore mutex underscore init. So ampersand mutex and null, no value first while in the initialization. And then for the pthread, this is for creating and initializing the condition variable pthread underscore cond underscore init. And then we have ampersand cond variable and null for its parameter. So thread waiting for the condition of A is equivalent to B to become true. So this is what we're going to use. So pthread underscore cond underscore wait and then its parameter is ampersand cond underscore var and ampersand mutex. And then thread signaling another thread waiting on the condition variable. So this is the code that is to be used. We have the pthread underscore cond underscore signal and its parameter is ampersand cond underscore var. Okay, we have POSIX and we also have Java synchronization. So Java provides a rich set of synchronization features such as Java monitors, re-entrant locks, semaphores, and condition variables. So for Java monitors, so every Java object has associated with it a single lock. If a method is declared as synchronized, a calling thread must own the lock for the object. If the lock is owned by another thread, the calling thread must wait for the lock until it is released. And then locks are released when the owning thread exits the synchronized method. So this is the bounded buffer Java synchronization. So we have this code. So what is this code doing? So it implements a solution to the bounded buffer problem wherein the producer and consumer invoke the insert, the insert and remove methods respectively. So we have the insert and remove method. Okay, next is we have a thread that tries to acquire an unavailable lock is placed in the object's entry set. So for this illustration, if the entry set for the lock is not empty when the lock is released, the Java virtual machine arbitrarily selects a thread from this set to be the owner of the lock. So when it is said arbitrarily, it is meant that the specification does not require that threads in this set be organized in any particular order. However, in practice, most virtual machines order in the entry set according to a FIFO or the first in, first out policy. Okay, next is similarly, each object also has a wait set. If there is an entry set, there is also a wait set. So when a thread calls wait operation or function, it releases the lock for the object. The state of the thread is set to block, and the thread is placed in the wait set for the object. So this figure illustrates the entry and wait sets for a lock. And then a thread typically calls wait when it is waiting for a condition to become true. So how does a thread get notified? So it is notified by means when a thread calls notify function. So an arbitrary thread T is selected from the wait set. T is moved from the wait set to the entry set. Set the state of T from block to runnable. T can now compete rather, to check if the condition it was waiting for is now true. Okay, next is we have the bounded buffer for producer and consumer. So, if the producer calls the insert method and sees that the buffer is full, it calls the wait method. So this call releases the lock, blocks the producer, and puts the producer in the wait set for the object. So, because the producer has released the lock, the consumer ultimately enters the remove method where it frees space in the buffer for the producer. So, next is we have the Java re-entrant locks. So, it is similar to mutex locks. The finally clause ensures the lock will be released in case an exception occurs in the try block. So, lock key is equal to new re-entrant lock, then key.lock. So, we have this try. Then, if you have this try, then the process will enter its critical section, and then finally clause, and then key.unlock. It's just the same as it is said. It is the same with mutex locks. So next is we have Java semaphores. So constructor is semaphore, and then its parameter is integer value, so usage. So semaphore sem is equal to new semaphore, then 1 try sem.acquire. If the semaphore is acquired, so it will undergo the critical section, and then catch interrupt exception if there is an error, and then finally sem.release. Okay, next is we have the Java condition variables. So condition variables are associated with an re-entrant lock or with a re-entrant lock. Then creating a condition variable using new condition method of re-entrant locks, such as this is the keyword. So lock key is equal to new reentrant lock, and condition convar is equal to key dot new condition. So a thread waits by calling the await method and signals by calling the signal method. So example, 5 threads number 0 to 4, shared variable turn indicating which thread's turn it is. Then thread calls do work function when it wishes to do some work, but it may only do work if it is their turn. If it's not their turn, they should wait. If it's their turn, do some work for a while. When completed, notify the thread whose turn is next. And then these are the necessary data structures. So we have lock is equal to new reentrant lock. So this is Java. The code is Java. Then condition, an array convars is equal to new condition. Then, of course, 5 threads. So it's 5. And then we have a for loop. For int is equal to 0, I is less than 5. Increment I by 1. So convars I is equal to lock.new condition. So this is the code for the example that we have on the previous slide. So only the thread whose value of thread number matches the value of turn can proceed, and then other threads must wait their turn. Okay, next is we have alternative approaches for synchronization. We have transactional memory, Openmp, and functional programming languages. So for transactional memory, so consider a function update that must be called atomically or uninterruptible. One option is to use mutex locks. So we have void update function and then acquire. And then for this part, modified share data and then release. And then a memory transaction is a sequence of read-write operations to memory that are performed atomically. A transaction can be completed by adding atomic S, which ensures statements in S are executed atomically. So again, this is the void update function, and then we have an atomic keyword here. So it means that it should be performed atomically or there is no interruption. So for Openmp, so Openmp is a set of compiler directives and API that support parallel programming. So again, they're using void update but would have a parameter of int value. And then the number sign pragma on critical. And then count plus is equal to value. So we're going to add the count and value and then stored the sum of count and value to count. So the code contained within the number sign pragma OMP critical directive is treated as a critical section and again performed atomically. Okay, for functional programming languages. So functional programming languages offer a different paradigm than procedural languages in that they do not maintain state. Variables are treated as immutable or cannot be changed, of course, and cannot change state once they have been assigned a value. So there is increasing interest in functional languages such as Erlang and Scala for their approach in handling data races. So it is we already concluded our lesson in chapter 7. So I hope that you've learned something from this chapter 7, the synchronization examples, by showing the classical problems of synchronization such as bounded buffer problem, the reader-writer's problem, and the Dining-Philosophers problem, and how does the different systems have their own synchronization techniques. What are they using in the system? So if you do have any questions, so please feel free to comment below, and please do not forget to subscribe to my channel. So thank you very much and good day.